Lepton flavor physics. Right, please take it away.
All right, thank you very much. So welcome back, everybody. Just to remind us where we left off last time, and also because once you start writing the CKM matrix, you just want to keep doing it again and again. Let me write it down in the Wolfenstein parameterization. So last time, I think we ended up talking about some of the tests on this picture from not only the kaon sector, but also the B systems, the BD system and the BS system, as probed at the B factories, as well as the Tevatron and the LHC, especially LHC-B. I just wanted to start with sort of current numbers for what these four parameters are, according to the PDG. And here you have to be a little careful because when one goes to the sort of the higher order corrections, there's different conventions for how you define them. So one convention that I'll use here is to just strictly define lambda as VUS itself. So in other words, the 1-2 entry of this matrix. And that means that when you do the higher order things, you sort of specify that that entry doesn't change. And so that's going to affect the higher order corrections. I just mentioned this because, for example, if you just go to the CKM determination of parameters in the PDG, they do not use that convention, although they quote numbers both for their convention and for this one. This one is the one I've sort of seen more in flavor physics literature over many years, but maybe it's evolving to the new convention of the PDG folks. In any case, the lambda, which is related to the Cabibbo angle of the Quark sector, this is 0.22465. Plus or minus 0.00039. And these are basically CKM fitter and UT fit are the places to go. These are the two groups that do the fitting of these parameters. The A is basically order 1, it's 0.832 plus or minus 0.009. Rho bar, okay, let's remind ourselves, rho bar and eta bar are just these quantities times 1 minus lambda squared over 2. Rho bar is 0.139 plus or minus 0.016, and eta bar is 0.346 plus or minus 0.010. Okay, so we can see there's a fit to this picture. I also talked some about extracting angles from the unitary triangle. So let me make my attempt once again to draw this thing in a somewhat readable fashion. So if you remember, here's the triangle. This is the angle beta. This one's gamma. This one is alpha. And beta is the one that was extracted from the beta psi k short measurement. And it's very, very well known, given by these fits. Whereas the alpha is one gets basically from looking primarily at beta pi pi decays, as well as beta pi rho and beta rho rho. These are a B to U transition. So notice this one is B to C. Remember, the J psi is basically the charmonium. And B to U is a tree level process, just like B to C, but it's more CKM suppressed. So then there's also B to D, basically penguin diagrams, meaning the loop diagrams, that can come in, and they have similar suppression. And what that means in practice is that the alpha angle is much harder to extract than the beta angle. Similarly, the gamma actually comes from B to D K types of decays and also has its own set of theoretical uncertainties in there. Nonetheless, one can do fits. Right now, the picture looks like the triangle is closed. One has beta 22.2 degrees, plus or minus 0.7. So known to basically within a subdegree, whereas the alpha and the gamma are basically known maybe to within order of 5 degrees or so, with alpha see, I can read my own handwriting. I think this is 84.9 degrees plus 5.1 minus 4.5. Okay. And these are at 68% confidence level, the alpha and gamma in particular. Okay. Gamma is, I think this is 31. My writing is terrible, so I can double check. If I really mean something else, I'll let you know starting tomorrow. Or someone can check now if you want. Okay, I'll put degrees. So less well known, but if one looks at by going, for example, to these bidding websites or looks at various talks given by those practitioners, what you see is there's been great improvement over the years, even just to pin the alpha and the gamma down to this type of range is it's a very big advance in the field. And this will only continue as there continues to be the next generation B factories and other experiments continuing to pin these things down. Okay, so that's sort of where we are with the CKM. And we also talked last time, I talked about meson mixing. I sort of talked about the KK bar system. And of course, in the B factories and at LHCb, we also had the BD mixing and BS bar mixing, which have been measured. So there are constraints on the unitary triangle diagram from, for example, delta MBD squared and delta MBS squared, etc. These diagrams all look very similar, right? So remember, we have things that look like the following, and to standard model, we're going to have basically, here's a, let's say a D or an S, and here's a B, and then we can connect them with some W's. And there's really U, C, and T in here, but let me just put the top in because it's going to be the dominant one in the B system, the T. Okay, and then here we have this. And over here we've got B, and we've got D or S, depending on whether it be D or DS. And so these things can then go into an effective operator, right? Like so, where here's the D, for example, or the S, here's a B, right? Here's a B, and then there's the D or S. And you can write down the effective Hamiltonian for these objects. So for example, for the BD system, the effective Hamiltonian goes like the following, and I'm not going to include all the prefactors, but basically we're going to have a GF squared, and then we're going to have VTB star VTD, okay, quantity squared, and then here's the operator BL bar, gamma mu DL, and then there's another one. So, and notice that this basically goes like lambda cubed in the parentheses for the BD mixing. For the B sub S mixing, so this is BB. For the BS, we're basically going to have the same sort of thing, except for now we're going to have BTS and VTB, okay? And then we're going to have B left, and S left, etc. Okay. So this one actually order lambda squared, okay? So it's a little bit stronger in terms of CKM suppression. And so just as we talked last time about the kaon system and the meson mixing, we can do the same for the Bs. Now the kaons were a little bit special, as I talked about last time, because it just happens, I mean, we're much lighter objects, and in particular, the kaons are such that there's not that many decay channels open to them, comparatively speaking. So we had very different lifetimes for the two mass eigenstates once we took into account the mixing. That's why we call them K long and K short, right? K short being short because it can decay right away to 2 pions dominantly, whereas the K long has to basically go through a sort of CP violation type of effect to be able to do that. In the
Sorry, there's a question in the.
yeah, beta, please interrupt anytime. Yes.
Sorry. The question is, isn't beta something around 70 degrees?
Isn't beta 70 degrees? I don't think so, right? Sine 2 beta is about 0.7, right? So 0.7 is, you know, yeah, no, beta is, I think this is right, okay? Yeah, I don't think it's 70 degrees. Sine 2 beta is 0.7.
Actually, 70 degrees is quite close to 90 degrees, and the way you've drawn it, beta is a pretty small angle, like
yeah,
well under 45
right.
degrees.
Yeah, because the sides are such, right? So that's the alpha and the gamma that are more open. Yeah.
Yes. Someone else says, I think gamma is around 70 though.
That's possible. I may not have written the right thing. Yeah. Yeah, I think you're right. I know that I'm looking at my terrible handwriting on my notes. I think that what I thought was a squiggled 3 is probably of this. Yeah, that's probably better. Yeah.
Okay, thanks.
Thank you. Yeah. Okay. So let's talk just a little bit about the formalism of the meson mixing. Okay. In particular, I just want to refer anybody interested in learning more about this. I'm just going to give little details. I mean, just a tiny rough picture. Really should refer to any of the reviews, lectures by Yossi Meir. He has a lot of them, and they all have this part, and they also all have lots of extra interesting details depending on which set that you're looking at. They're all absolutely worth doing, and he has all sorts of details in there. So this is just the sort of cartoon version. But I just wanted to give you a feel for kind of the notation because it shows up in certain places. So the idea is really the following. We want to think about...
Sorry, there's one other question.
Yeah, sure.
Is the top quark the dominant contribution in the box also for B to D transition?
Yeah, it turns out it still is. Of course, in practice, when you do the calculation, you include everything, but it is going to be the dominant piece. Yeah, it's related to the sort of notion I talked about last time where the Jim cancellation sort of is much less operational for the top because of the heavy split, the large split it has with the other up-type quark masses.
Mm-hmm. Oh, and then related to the previous question, there's a comment that PDG 2019 says that gamma is 73.5.
73.5,
degrees.
Great. That's fine, good. So I think this is within that range. Yes, okay, good. So let's talk about now I'm just going to take two neutral mesons and I'm just going to call them B0 and B0 bar. So it could be D or S. It could also be D mesons or Ks. It can be any of them you want. Let's just focus on these just for notation's sake. And so how one defines these, the evolution of these guys and their mixing is you basically can write down a Schrodinger type equation, right? If you like, let's just sort of make them in ket form, so they're really functions of time. And then there's, when I talked about the kaons, I talked about a sort of 2x2 matrix that was there, which you know, encoded the fact that the kaons could mix through the weak interactions. Here, what we also want to do is to recognize the fact that these things can decay. So we should really add a complex piece to this Hamiltonian to represent the fact that decays are happening. Okay, so we can then write out B0 and B0 bar, like so. Okay, and then basically, last time we talked about for the M hat, and you can do the same for the gamma, you would do the calculation based on these box type diagrams in the standard model for the various entries. The point is, once you have those, you want to diagonalize the mass matrix, and you're going to get eigenvalues B, light, and heavy. And those are always written in the following sort of notation: P times B naught plus or minus Q B naught bar. Okay, where of course then the get myself a little bit more room. Then the
is gamma Hermitian here? There's the question.
Gamma is Hermitian, yes. That's right. We've just put out the I specifically to represent the fact that the gamma part's representing the probability of decay. So that's why we're going to have a complex piece, if you like, to our Hamiltonian. Okay. Yeah, so we have now M minus I gamma over 2, basically acting on P plus or minus Q is equal to M light or heavy, the mass eigenvalue, minus I gamma light heavy, the decay on the P plus or minus Q. So, okay, and you can from there solve. You can, for example, obtain Q over P is equal to minus 2 M12 star minus I gamma 12 star over, let me write delta M minus I over 2 delta gamma, where delta M is, of course, going to be equal to M heavy minus M light. Delta gamma, same, gamma heavy minus gamma light. Okay. And now in the B system, it turns out that the gamma 12 absolute value is much, much smaller than the M12 absolute value. So the delta gamma is actually much smaller than delta M. That allows for certain simplifications in both B systems. That happens to be the case. So now that we have some formalism for the mixing, we can then discuss, we can measure many different types of decay amplitudes. And so here's the sort of usual set of things in the usual Yossi-Neer notation. So let's talk about the amplitude for the B naught to decay to some final state F. So let's write FH B naught. Okay. And then we can also talk, for example, about the decay, and I'm going to write this as A bar F. That would be the decay of B naught bar to the same final state F. Of course, then we can also have, if you like, A F bar. That would be the decay of the B meson B naught to the F bar final state. Okay, and in principle, we could have the A bar F bar, which would be decay of B bar to the F bar. Okay, so depending on the situation and the final state, you can have different ones of these possibilities, and you can measure many of these things depending on the process. So how it's typically classified, is that there's 3 different ways you can measure CP violating effects. So one is CP violation in mixing, so mixing only, and that turns out to be signified if Q over P, that ratio, is not equal to 1. And if that happens, then what can happen is that you can get what we call wrong sign decays induced by mixing. So in other words, if usually a particular particle is going to decay to a particular final state with a particular sign of one of the final state particles, and then its anti-meson would decay to the opposite sign, then what you can have is if you have mixing between B and B bar, then you can induce the wrong sign of that final state by first taking your initial meson, mixing it to the other one, and then decaying. Okay, so that's the CP violation in mixing. There's also CP violation in decay. And the CP violation of decay, this is one of the things we're calling direct CP violation last time. That would be if the amplitude A bar F bar, as defined there, over AF, okay, absolute value is not equal to 1. Okay, so this is sort of the clear statement that the conjugate 1, right, the B bar going to F bar, if CP was not violated, you would expect that to be equal in magnitude to the amplitude of B going to F. And for example, the charged mesons, we're talking here about neutral ones, but we can also have charged B, D, and BS mesons. Those are only going to have this type of exhibit, this type of CP violating effect, because obviously these charged states aren't mixing. Okay. And then finally, there's the last one, which goes by the nomenclature usually of CP violation in the interference of decays with and without mixing. Okay. And there it turns out the figure of merit is a quantity that we're going to call lambda F, and that's defined to be Q over P. Amplitude A bar goes to F over A to F. And if this combination is not equal to 1, then we're getting CP violation in the interference of these decays with or without mixing. And in particular, it's this type of CP violation here that turns out to be the type of process that one is looking at to extract, for example, sine 2 beta from the CPA symmetry. Okay. So these are just to kind of orient you if you would like to look into more of these things, and you can look at the many, many different processes people are looking at. Basically, all these different types of CP violating processes have been observed. They're supposed to all happen in the standard model, whereas before, the standard model picture of CP violation was sort of basically, I would say it's pretty robust. It doesn't mean there's absolutely no room for new physics, okay, but it looks pretty strong so far. Before that was really known, which was in the era before the B factories and all these advances in the system, it could be that you could have a theory which only has CP violation and mixing, for example. That was Wolfenstein's super weak theory, etc. You could have different possibilities than what was in the standard model. So we see the standard model is basically quite robust. And in fact, if we sort of take that further, and of course there's a caveat about the B system anomalies I'm going to get to in just a minute, okay? That means generally there's going to be very strong constraints on possible new physics in basically the meson systems, okay, that we probe so well. And this is what goes by the name new physics flavor puzzle. So just to give you an example, suppose we consider some arbitrary scale associated with new physics, okay? If new physics comes in with sort of order 1 flavor violation, remember in the standard model, we do not have that generally. We have flavor has to change via the W. There's CKM suppression because the Quark mixing angles are small. There's the GIM suppression. There's all sorts of ways in which certain processes are very much suppressed. So if you bring in new physics, generally we don't have all those structures put in place in the same way. And so if we just imagine order 1 flavor mixing, then you can look at the possible limits on what this new physics scale could be when you look at the various different meson systems. And then the current numbers for this, and you can look, for example, at the heavy flavor averaging group, who looks at, for example, all sorts of constraints, again, global fits, etc. So what you see is arbitrary new physics with order 1 flavor violation is going to have a limit of, it must be greater than 10 to the 5 TeV for the kaon system, so the SD sector. There's also for the D mesons, order 10 to the 3. This is including all possible operators that can come in. Certain operators are much more robustly constrained than others. This is just imagining that all of them that could happen with order 1 coupling strength. This would be the type of bounds you would have. Okay, so just to be sure we interpret it this with some understanding that this does not mean every single new physics operator has this scale. It means that look at all of them that could happen if you just allow not only left-handed sort of currents, but also charge currents, but also all sorts of other types of interactions and Lorentz structures and etc. Then you're going to get these types of limits for whatever the strongest ones are. So the D system is 10 to the 3 TeV. And for the 2 B systems, 10 to the 3 again, TeV. This is for the BD. And 10 to the 2 TeV for the B sub S system. Okay. And so the question then, of course, is suppose, as many of us have long supposed, that maybe there should be new physics coming in at a TeV scale because of other issues we'd like to resolve in the standard model, like the hierarchy problem, etc. Okay, now whether or not we should all be thinking those thoughts still after all these years looking for things is another whole line of questioning. But if you imagine that there is new physics at the TeV scale, then the question becomes, how do we have to write down theories in which these order 1 flavor mixing parameters are controlled very strongly. You can see the biggest place where they're important is in the kaons, but they're pretty severe everywhere. Okay? So this is this new physics flavor puzzle. Why are there such strong constraints? Right? Why aren't we seeing any effects? Because generally if we add in new physics at the TeV, we're going to just literally obliterate the beautiful sort of flavor structure of the standard model. Okay, and I will get back to that in a minute. We'll talk about that later. But what I would like to do is, I'm just telling you, standard model looks pretty robust. So let's talk about the places where there are tensions with the standard model. Okay. So let's talk about the B-physics anomalies. Okay, and again, this is a kind of a cartoon version. There's expert practitioner reviews available. That I recommend very much. So Altman, Manshofer is a good place. Another person with a lot of nice overview papers is Dory. I guess let me just include some other friends here. Hiller, Bernstein, and there are many others. Okay. So here I'm just going to give you kind of an overview, and if you want to see a lot of details, and there's a lot of details here, I would recommend you check out those things in more detail. So
Question in the chat. Sorry, a question in the chat about I guess about the scale of flavor violating new physics. What if it comes in a non-perturbative way, like some topological defect?
Oh yeah, no, that would be, I would guess, again, it would matter very much on what type of operators are generated. And essentially at the level of sort of an effective Hamiltonian point of view, a big part of it has to do with, right, there's the mass scales of the new particles, and there's also the coupling strengths, et cetera, of the new states. So they would all have to sort of combine, and the point is, at this point, certain operators, the most stringent constraints are at that level in these systems. So that would have to be looked at, I would imagine, on a case-by-case basis.
And a second question, I don't understand how flavor physics is able to put strong constraints at 10 to the 5th TeV. I thought typically low energy theories are insensitive to higher energies.
Yeah, no, the reason why is because of the fact that standard model has a number of very specific properties to it in terms of how flavor can change. So in particular, it's only changes at the charge current via the W exchange. That's controlled by the CKM, which we've seen parametrically has very small off-diagonal elements. And furthermore, it's the sort of SU2 left, V minus A structure of the standard model, which tells us that generally we can have GIM type cancellation. So there are many processes that in general, because of the properties of the standard model, are very, very much suppressed. But if you add in some sort of arbitrary physics at various scales, it's going to overproduce those things because those cancellations just won't happen, right?
So even though it's still...
physics can show up here because it's taking a place where standard model is very, very much suppressed, okay, because of specific properties of it. And if you add something where it doesn't obey those properties, it can come in at much, much higher strength. The electric dipole moment is another example, right? So I'm just saying standard model predicts vanishingly small electric dipole moments, well away from even current limits, even though the limits on the EDM are just, people are doing an amazing job continuing to push those and trying to see if we do have an EDM. But in the standard model, it's extraordinarily small because it's a CP violating process, but it's also something that connects first generation to first generation, if you're thinking about the electron or the neutron or whatever. And the point is, in the standard model, CP violation has to enter through flavor change. And we saw that flavor change, that CKM phase is actually removable if we only had two families. So that means a lot of CP violating effects, you really have to kind of cycle through all three families in some way. And maybe one term is more dominant than the other, but they all kind of have to be there, right? So that's how these things can be such a sensitive probe.
Thank you.
Okay, all right. So let's talk about tensions with the standard model in semi-leptonic B decays, because this is where they've been seen. Okay, now there's several of these tensions, and none of them are individually at the discovery level. Combined, they've been persistent over quite a few years now, some of them, at 3 sigma-ish, sometimes a little bit higher, sometimes going back when people revisit and new data, new calculations, et cetera. Okay, and Okay, and these things have been seen. For example, they were seen. Some of these things were seen at Babar and Bell, which are the first generation B factories, which basically shut down operation in the sort of near 2010 sort of time frame, and also at LHCb, and now also at Bell too. So it's not just one experiment with one thing, it's several, and it's in a certain class of things where the B is decaying that semi-leptonically. So here's the first set. So the quark level transition would be B to C, lepton, neutrino. Okay, so notice that would be a charged current, three-level sort of process in the standard model. And the quantities of interest that are looking at are actually ratios. I'm going to get RD, and then there's a star because it can either be a D or a D star. That's the branching ratio of B to D star, tau nu, over the branching ratio of B to D star, L nu, okay, where L is both electron and muon for Babar and Bell, and L is just a muon for LHCb. Okay. So that's one of these, and the main issue here is that these things, because they're ratios, the thought is that hadronic uncertainties, which sort of are extraordinarily important for calculating, for understanding any of these branching ratios, etc., calculating them in the standard model, the thought slash hope is that when you take the ratios, things are going to be much cleaner, theoretically, because certain things are going to be common to both and cancel out, okay? And so what one finds generally is that one has basically higher values from the experiment, okay, than what's predicted in the standard model by about 3 sigma, okay? So that's one set, and I could look up and write down all the numbers if you want for exactly what they are, okay, but the point is they're a little bit higher experimentally than what the standard model calculations suggest they should be. Okay. I'm having trouble going down. There we go. Okay. Now the next set are in the processes, quark process B to SLL. And that's, as we know, the B to S transition is a rare decay, right? It's a neutral current. So it's a rare decay in the standard model. And here there's a ratio RK and also an RK star. Okay, so we're just going to lump them both together. And this one is the branching ratio for B to K star, K or K star, mu plus, mu minus, over the branching ratio of B goes to K star, E plus, E minus. Okay. And this one basically is lower than the standard model prediction. In particular, the one really cares about most, I would say, is the K star object, in which case one measures it in different bins of a quantity called Q square, which is the invariant mass of the muon pair. Okay, so the idea is that it's basically less than the standard model prediction, again by a couple of sigma. And let me try to be a little bit more quantitative about that, just a little bit. Okay, so one of the things that and this is an LHCb, and it's been around for a while now. Okay, so the idea is sort of somehow too few. Either it's too few muons or too many electrons. And in terms of new physics, ideas for if it's due to new physics, what it could be, most attempts seem to suggest that trying to make it modifying the muon coupling versus the electron coupling seems to be a little bit more successful, but it's still not definitively known which one would, both are possible, okay? So these have been around for some time, and what's relatively recent is a particular angular observable. And the B to K star mu Okay, so that what happens is then the K star decays to a K and a pi. So we have as a 4-body decay. And there's basically a particular observable where we're seeing discrepancy with the standard model in certain bins of Q squared. Okay. So let's just think about what the differential decay rate might be a function of in such a situation. So basically, this is going to be a function of Q squared, and then let's try to draw a figure. Okay, so let's imagine here's a B, okay, and let's say over here are the, so we're going to try to draw things if this is the typical picture, okay. Let's draw an angle theta of L. So that would mean in sort of the frame where we're sitting there, so often it's sort of drawn like this, okay. This is that angle between the muons, and they're sort of frame for the decay part. Then there's over here, there's the kaon, there's the k and the pi. Okay. And here's, like, for example, suppose that's the k and the pi. And then there's an angle that's traditionally called theta k star. Okay. That's basically sitting on the k star. And then it decays to the k and the pi. So it's in that sort of frame. And then sort of draw the picture again, sort of signifying that that angle is measured in that frame. And then there's going to be an angle phi that's sort of relating the frame. So we have q squared, theta k star, theta L, and phi. Okay. And so you can write out the differential decay rate in terms of these quantities, then it's just a sum, a basis of all kinds of angular functions that are evaluated at each q squared. And I'm not going to write down that full expression because it basically takes a page. Okay. It's huge. It's just imagine taking something and basically looking for a basis of these angular functions like YLMs, except for we have many more variables here. And so what people have very cleverly done, and this is a long story about which I'm really not qualified to comment in detail on methodology, is to try to come up with an optimized set of angular observables when you expand out this differential decay rate in terms of these angular functions. And you want to optimize the angular observables to try to minimize your hadronic uncertainties, which is a non-trivial business, okay? So a particular one of these variables is something called P5 prime, okay? So this is part of a set of optimized angular observables that basically are being measured at LHCb and also at Bell, which is really quite something. And it turns out there's a discrepancy with the standard model.
Here's an interesting question.
Yes.
Are those angles Lorentz invariant or not? If no, how do we check them in experiments?
That's a really great question, and I am not the right one to answer it. Yes, there's a whole section of the PDG, for example, that talks about the angular observables in the B decays, and you can read. I think that there's all kinds of technicalities that one has to do to, I honestly, I don't even know the answer to that. I would guess not, by the way. Okay, because we're talking about this one is in that frame, and this one is in the other frame, and this other thing here, right? So yes.
Yeah, I think they're not. But I think if you can reconstruct what the BMES on the original BMES on rest frame is, then you can
try to figure them all out. Whether that's possible experimentally, it's not obvious to me at all. Yeah.
Yeah.
In fact, one sort of kind of funny thing I noticed when I was first learning about this P5 prime stuff a while ago, I remember just one time just literally typing in Google, what is P5 prime? You know, because you see it and you're like, what is it? My God. And then there's somebody actually has a talk, I think it's a KITP talk, and I'm forgetting the particular lecturer's name. It was a general talk on flavor. And literally his first slide is, what is P5 prime? And he has a much better version of this picture and a huge formula trying to explain the logic. Yeah. But anyway, yes. So the point is, the P5 prime is only one of many, many sort of amplitudes associated with when you expand out the differential decay rate in terms of angular functions of this type. There's many, many terms. It just happens that in this case, there's a discrepancy with the standard model in two q-squared bins. And each one is about 2.1, it's like 2.5 sigma. One is 2.9 sigma. And this is a 2020 update. In fact, at a flavor conference that was just had this spring, post COVID-19 shutdowns everywhere. It was supposed to be in Paris, but they all had to just use Zoom instead. Okay, that those are updated numbers that were first reported there on this observable. And when you sort of put this together, right, with some of these other features, then you sort of have an overall discrepancy with the standard model of about 3 sigma. Okay, so the point is, this has been around for a while. The P5 prime, I think, was a couple of years ago when they first sort of saw these discrepancies in the bins. Those discrepancies are the 2.5 sigma, 2.9 sigma, I believe, are a little bit smaller now than they used to be, but they're still there. And in fact, the overall sort of fit, overall tension actually went up a tiny bit. Okay, so the main point is, we can see that all of these things are sort of telling you that if these anomalies are really about some sort of new physics and not due to hadronic uncertainties or issues with the experiment or etc., then what they have are basically implications for lepton universality. Remember, lepton universality just sort of means that, you know, when you have like a W or a Z or whatever, basically with the leptons, whether that's E, mu, or tau, right, it should basically have the same kind of coupling strength. Okay, and so this is the thing to sort of wonder, is this somehow a place where interesting new physics is happening? Okay. Now, I'd like to start really by talking about the B to S, L plus, L minus. Okay, and let's talk a little bit about the effective operator description. This thing. Okay. And so here, let me refer also to some very nice papers. Hiller and Schmaltz, who I understand Schmaltz has lectured here at this TASI, have a very nice paper from 2014 on some of this analysis. And again, some of the other references up there, Altman's Hopper and Isidori, they also have looked at this problem. So let's talk about then, right, what is the process that we're looking at essentially? Let's just look at the sort of important sort of effective operator that you have. You can sort of imagine it sort of looking like so. There's some sort of blob, and then there's the B goes to S, L, L, okay? And we know, for example, in the standard model, we can open this thing up. Here would be, for example, a W, here's a T. Okay, this could be a Z here. Well, that's a terrible diagram, but whatever, I'll just leave it. Okay. You can also have others. So B, T, S, W's, there's a neutrino, etc. And as I said, these are the standard model ones. Okay. And standard model says that these places where the L couplings come in should be the same, depending on whether or not you have an electron muon or a tau. So let's talk about then the effective Hamiltonian of such a process. Okay. And this is traditionally written as follows: minus 4G Fermi over root 2. Then there's a alpha over 4 pi, where alpha is the fine structure constant here, VTD, VTS star. And then there's going to be a sum over possible operators, CI, those are the Wilson coefficients. And then there's operators OI. Okay, these are really all scale dependent. Okay, in the standard model, the relevant operators go by the names of O9 and O10. So their Wilson coefficients are C9 and C10. And they look like the following: S L bar gamma mu BL, L bar gamma mu gamma 5 L. Okay, so gamma 5 part is just for the C10. Okay. And by the way, if you are interested in seeing all kinds of details about this approach of calculating these effective Hamiltonians for flavor mixing, then the canonical review is by Bukala, Burris, and some collaborators, and it's from 1995. And if you're looking into this subject, eventually everybody refers you precisely to this, because this is where all the language is essentially spelled out. Okay, so in the standard model, C9 and C10 are given by the same magnitude but opposite in sign, because the standard model is V minus A structure. Okay. Whereas now, if you have standard model plus new physics, then you're going to generally have some CIs, which are going to be the CI standard model plus the CI of the new physics, whatever that might be. Okay. And you consider all the operators up to dimension 6, 4 Fermi operators consistent with gauge invariance. And in particular, you'd also want to have lepton specific ones, meaning different label depending on whether the lepton in that operator, and those operators are E, mu, or tau. Okay, so there's actually a lot of different possible operators. And they comment, of course, also that at the end of the day, what one really also needs to have as an important part of these processes is the Hydronic matrix element, which one obtains, for example, by taking K star tau L, H effective B, right? And so this thing is going to be basically the same sort of stuff we had above, except for now the operator, right? You have to fork out this non-perturbative matrix element with these Quark operators inside. Okay. So they said there's many, many studies of this. It turns out that if one wants to explain, for example, the RK star, okay, you need basically, you need about 20 to 25% of the standard model contribution in new physics. And because there's so many new operators that you can write down, if you really just try to do just a fit, right, this is where you can look, for example, at work of Hiller and Isidore and Almashofer and various other experts. These are very, very complicated. In practice, there's probably just too many possibilities, but one of the basically the ones that seem the most preferred by the fits are either new physics in C9, okay, or new physics in C9 and C10, with C9 new physics also equaling to C minus C10 new physics, just as a smaller proportion of it compared to the standard model contribution. So in other words, one of the sort of preferred solutions, and if you look at the most recent discussions, I think the recent discussions, Altmannshofer has a review of this in his talk in this Paris meeting, literally from a month or two ago, claiming that it's actually the C9 and C10 solution with the this is a SU2 left invariant relation, right? That we're going to have the vector and the axial vector related in this sort of way, okay? So this seems to be the preferred option at this point. And furthermore, basically what one really wants is also C9 new physics, basically less than 0 preferred, okay? And interestingly enough, it leads you down an unexpected set of roads in model building, because many of our usual suspects, or if you round up the usual suspects for TV physics, it turns out getting the C9 to be kind of greater than, absolute value to be kind of greater than or equal to the C10. In SUSY, for example, that doesn't really work very well, in fact, because the C9 over C10 ratio that you generally get from adding in superpartners generally is small, right? So it's not going in the direction that you really want it to be, okay? So what people have focused on, there's many different possibilities for what you can focus on, but let's focus here on the more straightforward ones. So we're going to, the postulate is from new physics, okay? And you can look at new tree level mediators. One could also consider models where you have loop level mediators. If you have tree level mediator, right, it's going to give you a different kind of bound on the mass that you might need, for example, in the coupling compared to if you have a loop mediator. Okay, but let's focus on the tree level possibilities. And there's basically two categories. One is a Z prime, okay, and another one is the Lepton quark. And there's been lots of papers written to explore both of these possibilities. And of course, for the Lepton quark, what we're interested in is the specific set of Lepton quarks that can contribute to the C9 and C10. Okay, there's lots of Lepton quarks you can write down just given standard model quantum numbers. Some of them only contribute to right-handed fields and would not couple to right-handed fields and would not give you significant contributions to C9 and C10. Okay, so let's talk about each one of these sort of in turn. How about let's start with Z prime. Okay, I personally like Z prime myself. Okay. And the idea is the following. Let's just have a flavor changing Z prime. Why not? So there's some coupling strength. Right. And here's the Z prime there in the tree diagram. So we can see that effects here are going to depend on the product G prime B S, G prime mu mu. But one thing you have to remember right away is that you have to worry about BS mixing, because notice here I wrote BS on the top line, but I could easily just write a BS, another BS line on the bottom line with it flipped, and you could get a contribution to the B meson mixing, which so far doesn't allow for much wiggle room for new physics. Okay, so generally because of this, BS mixing constraint, generally you're going to want G prime BS much less than G prime mu. And like with all sort of models of Z prime, everything depends on the coupling strengths, right? The size of it, right? Are they tiny? Are they big, etc.? And then also the Z prime mass. And so there can be a wide range of Z prime masses possible, anywhere from TeV to tens of TeV, depending on the size of the coupling you want to put in for these things. Okay. And generally, I mean, there's different ways you can do it. One of the things you also have to worry about is ZZ prime mixing, which is strongly constrained, etc. A popular solution here is basically a gauged L mu minus L tau. So in other words, lepton number mu minus lepton number tau. That's an anomaly-free combination, and it seems to be a way to sort of single out the mu object differently. Okay, so there's many scenarios based on this. Yes, go ahead, Heather.
Sorry, there's a question. The Z prime cannot explain the charge current anomalies, right?
That's right. So the answer would be for the charge current anomaly, maybe their Z prime might come in and multiply it also with a W prime or something that you would change that one. Yeah.
Oh, that's cool. Okay. And did you just say that gauging L mu minus L tau turns off the ZZ prime mixing, or?
No, I did not say that. I just saying that
sorry.
Z prime mixing is just going to depend on how you charge the Higgs, for example, with respect to the U1 prime, right? So the main point here is you want to worry about if you want to worry about anomalies of your U1 prime, then oftentimes it's useful to sort of cancel them. You're not adding new fermions, so basically what you just want to do is sort of cancel them pairwise, right? And so that's why an L mu minus L tau. It could be other combinations, but this one turns out to be sort of a favored model. And so there's a number of papers on that. That's kind of a good keyword if you like, okay? So, and of course, once you start turning on a flavor changing Z prime, you just have to make sure that other flavor constraints are satisfied. So there's some challenges, but you have some wiggle room to play, and there's lots of papers on this topic, really a lot, okay? So I would refer just generally to these Brinstein's Slack Summer Institute 2019 as a theory review of these new models, which is excellent. And it has a lot of referencing. Yeah.
Can I ask you another question? Actually, do you know if there's a B to K or K star tau tau decay? I think it should be kinematically allowed, but maybe it's so nasty to reconstruct that it's not measured.
I think it's allowed. I don't know if that's something measurable, if they have measured it. Yeah, I don't know yet. Yeah. But I haven't seen any data reported on it, but it's something to keep an eye on. Absolutely. Yeah.
Sure.
Thank
Thanks.
you. Yeah. So, okay, let's go on to, one could spend lots of time talking about the Z prime, but let's talk about the leptic quarks. Okay. Okay. And so these are another set of possibilities. So let's just draw a cartoon of what they can look like, right? So leptoquarks are objects that basically can have couplings between quarks and leptons directly. So for example, let's suppose we have BL and there's some sort of phi in here in the middle, okay? And then we have an SL over here. And so there might be some coupling, lambda BL, and then over here there's a lambda, sorry, SL. Yeah, there we go. A lambda SL. Okay. And basically, if you list all the possible leptoquarks that you can have, there's only a subset that can really couple only to the left-handed fields and can give contributions to the C9 and C10. And one thing you'll notice if you look at this literature is that, first of all, these leptoquarks all have sort of standard names that I'm not sure where the naming convention started, but they all have their sort of names. And so there's one called a U1 mu, and that's a vector, right? These things are vectors or they're scalars, right? They're coupling to fermions. And so there's a U1 vector leptoquark, which has SU3 quantum, SU2, U1 hypercharged quantum numbers 3, 1, 2/3. Oops, yes, I can write 2/3. There we go. Okay, so for example, the coupling might be lambda ij, q bar I, gamma mu, lj, u1 mu. Okay, that coupling. So people like this one. It's not the only possibility, but this one has sort of gotten most of the attention in this business, especially recently, because then the claim is that this vector leptoquark could also perhaps play a role in also looking at the charge current, the RD star as well, not just the arcade star. Okay, and so the thing to keep in mind with the leptoquarks is a couple of different things. First of all, the minute you have leptoquarks in your theory, first of all, there's pretty strong constraints on their masses from direct searches in the TeV-ish range. I guess not that much, infinitely much worse than every other new physics particle so far, right? But they also, in general, can lead you to proton decay really fast, okay? In fact, leptoquarks are a standard thing that emerge in grand unified theories. They're just generally there. That some prototypes would be the X and Y bosons of SU5, for example, for those who are aware of those objects. And the point is, those things, if they're light enough, they're going to lead to decay of the proton, and that's a big problem. So one has to worry about those constraints quite a bit. I would say, generally, as I said, there's huge numbers of papers of this type, okay, talking about the leptoquarks for these objects. Let me also just mention, since I didn't really talk about it that much, for the charge current ones, as I think Heather already asked a question, which was, you would need some sort of different object than just a Z prime, et cetera. And so those, you can also have tree level mediators. You could have a sort of WL prime, if you like, or you could have a WR prime, right? You could have all kinds of stuff depending on what standard model of quantum numbers the things really need. Okay. For the charge current ones, there's, I would say, a lot more kind of, it's a generally lower scales involved because of the tree level process, and so there's tighter constraints, so one has to worry. I would say generally, okay, there's some concerns. One is sort of keep the mass of the mediator light enough, because generally these mediators can have sort of arbitrary masses, sort of like the mu problem of the MSSM, if you like. So why is the mediator right there? By light enough, I really mean in the right sort of range to explain this. Okay, oftentimes there's no explanation for that in these types of models. And then another thing that's really sort of missing, although it's not too surprising to me that it is, because it's a very hard connection generally, was basically connection of these things to other BSN physics, such as, in particular, you might think maybe they could have something to do with the flavor puzzle, meaning the fermion mass patterns of the standard model, given that we're introducing flavor changing objects. It doesn't seem to be easy to make those connections either. Okay. So the point is, these anomalies have been persistent. They haven't been growing, but they're persistent. There's non-perturbative physics people are worrying about with great concern given these issues. They are difficult. Generally, there's a lot of challenges, apparently, with the hadronic uncertainties and these types of things. We'll have to wait and see. But interestingly, this may be the place where the standard model finally crumbles. It's a possibility. We have to keep our minds open. Okay. All right.
Lisa, there's another question.
Yes.
Actually, two questions. The U1 mu should be associated with some gauge symmetry, right? Is it involved with some kind of gauged flavor symmetry or something else?
Yeah, so when we talk about having the U1 mu minus tau, if you like, that symmetry, we are gauging it. And you might want to say, well, why is that particular, be like standard model cross, that particular gauge symmetry? So it could perhaps emerge from a bigger symmetry that might be used, for example, as a family symmetry group, et cetera. But I think it just depends very much on the scenario in which you're considering it, but yes.
There's also, one of the students points out that other combinations such as E minus mu and E minus tau are also anomaly free. And is there any specific reason to choose mu minus tau?
Yes, apparently there is. And I think that it has to do with the fact that now the muons are kind of playing an important role in all of these various anomalies. So apparently the mu minus tau is preferred. It's a good question. I don't know the answer off the top of my head. It gets into details that are a little bit beyond me, but I think that apparently that's the preferred one as far as maybe I'm wrong. I looked at the literature to try to see the range of different possible U1 primes. This one seemed to be the one that showed up more. But I can think more about that and try to get back to that question maybe tomorrow as well. It's a good question.
Another question, how light should this mediator be?
Oh yeah, so again, it depends deeply on these couplings, which are also unknown, right? So it's the usual kind of combinations, right? So when you're dealing with the tree process, they need to be lighter, right? The B to C processes, the tree level part, these things need to be lighter because you want them to kind of be in there kind of competing with standard model piece that's pretty big. Whereas the B to S ones, it's a loop transition. So in general, the new physics that comes in should be probably, it doesn't have to be as light and it generally could be heavier. It depends on the coupling strengths, which again are then not easy to independently, well, you can't independently determine them from just these processes. You'd have to somehow probe them another way.
Another student says, Patty Salam.
Yes, Patty Salam, absolutely. And people have been looking at that because this leptoquark is there in Patty Salam. Yeah, that's right.
Another question, is phi a scalar or a vector boson?
Well, in this particular cartoon diagram, it looks like a scalar because that's how I drew it. But I'm just saying you could have scalars or you can have vectors. Just depends on the coupling. When I wrote that coupling of the U1 vector leptoquark over there, you see I have a gamma mu in there. Yeah.
Yeah, okay. Thank you.
By the way, there's an excellent review on leptoquarks that I found very useful, and I should have written down the archive number so I could write it here so people who are interested can look. But it's from 2016, so I think if you sort of do like leptoquark 2016, you're going to find it, and it's extraordinarily systematic and helpful. So I recommend it highly. Okay. All right. So what I'd like to do now in the remaining time today and into early part of tomorrow is let's just leave this for now and say, wait and see. There may be something interesting here. Okay. Maybe, hopefully, that would be great if there were, okay? But let's go back to the notion that basically, as I told you before, just from looking at these meson systems, it looks like standard model is pretty robust. And then the question turned into, if we have new physics coming in, what's some sort of guiding principle for keeping these flavor violating, possible flavor violating interactions from sort of coming in there and destroying the standard model, the beautiful structure of the standard model that seems to be so consistent with what we've measured so far. And so this idea is some guiding principle, and it's not the only possibility, but it's a very interesting one that I'm going to spend a little bit of time on, is this notion of minimal flavor violation. Okay. So the idea is the following. Let's go back to the standard model, and let's just remember there's no neutrino mass here. It's a strict definition. Let's switch off the Yukawas. Okay. Then what you find out, if you switch off the Yukawa couplings, the theory actually has a huge global symmetry. I should go to the standard model. Switch off Yukawas. The global symmetry is really a U3 to the 5th. And this U3 to the 5th, I know for me, was the first time I heard about that was when I was at TASI myself listening to Lawrence Hall. And he says U3 to the 5th. So what is the U3 to the 5th? So this is the idea that we can take the 3 quark doublets and perform U3 rotations on them, as well as the right-handed ups, right-handed downs, leptons, left-handed doublets, and the right-handed lepton singlets. Okay, so sometimes we'll call this one U3 cubed, and this is the U3 squared L, for example, for lepton. Okay, so basically once the Yukawas are switched on, they're going to break this. Okay. I'm going to break this thing to U1 baryon number cross U1 LE cross U1 L mu cross U1 L tau global. That's a U1. U1 L tau global symmetry. Okay. And so basically any interactions that you have that break the SU3 portion to the 5th portions in particular are the flavor violating objects. Okay, you can see the U1s, there's some things where you have to be a little careful how you do the counting because of the fact that we know that the standard model obeys this particular global symmetry among the U1 factors. Okay, and so the idea is to say, okay, let's imagine that this is a real symmetry and let's treat the Yukawas as some sort of spurion field. So some auxiliary field that breaks the symmetry. Okay, so in the quark sector, we can then calculate with respect to the SU3, sorry, let's talk about the SU3 cubed for the quark and the SU3 squared for the lepton. So we can then write that the up-type Yukawa coupling, right, that connects the Q to the U. So this thing looks like a three bar, 1 under SU3Q cross SU3U cross SU3D. And similarly, YD goes like 3, 1, 3 bar. Okay, because now instead of the U, it's the D. Similarly, over here, we can write down the lepton Yukawa coupling, and this thing should look like a 3, 3 bar. That's sort of, so if we treat these things as some sort of auxiliary field, what we can do is we can formally restore the SU3 to the 5th invariance, okay, in this sense, okay, and we can then imagine that our new physics, whatever it might be, if we construct it from just the standard model fields and these spurion fields, YU, YD, and YE, then what's going to happen is that there's going to be a very precise pattern of flavor violation that's known as minimal flavor violation. So I know I'm kind of running short on time, but let me just try to take a few minutes to sort of finish up. Okay. So the idea is, okay, minimal flavor violation means all higher dimensional operators are constructed from the standard model and the Yukawa fields. And these are going to be then invariant And we're also going to assume no, what we'll call flavor diagonal, or really I should say flavor independent violation. Okay. So by flavor diagonal or flavor independent CP violation, I mean, remember the CP violation and the weak interactions of standard model is a flavor changing effect. There's no vertex that preserves flavor and is associated with CP violation. So when we have new physics, we could have those, right? Supersymmetry generally, for example, soft breaking terms generally will have those, and those are very much constrained by electric dipole moments because that's the thing that is suppressed in standard model because you have to change families 3 times just to go back, okay? So the idea then is that in such a theory, then all flavor structure is constructed, all flavor structure, I should say, what do I want to say, is from the ordinary Buchau couplings. And all CP violation is from the delta CKM, okay? And so what this means is it's going to tell you that the coefficients of certain operators that are going to be generated are going to be very much related then to the same types of suppressions that we see in the standard model. Remember the CKM suppressions, the GIM suppressions, the same kinds of things would happen then for the operator generated by the new physics, because the only way the flavor violation can happen is through the same couplings that were already there in the standard model. So this was sort of explored in detail in a famous paper 2002, and there were some earlier discussions as well where a little bit more restrictive, where they insist that all operators generated are only of the same form as the standard model operators, no new ones, okay? And you might say, well, how could there be new ones when we just sort of required that, you know, all the operators we have are from the standard model and from the Y? And the answer is that some new physics theories, for example, that is true, but others, for example, theories like the MSSM would have 2 Higgs doublets. For example, in limit of large tangent beta, where tangent beta is the ratio of the 2 vacuum expectation values of the Higgs doublets, then what can happen is there can be new operators generated because they're new sort of scalar operators that are not there in the standard model because we only had 1 Higgs doublet. Okay, so this is the idea of minimal flavor violation. And what people usually do, and I'll finish up in just a little bit, what people usually do is the following. Very often, because remember, oftentimes we're looking at external down quarks, and so the uptype big splitting ones are in the loop. So oftentimes one goes to a basis in which the downtype ones, downtype Yukawas, are diagonal. Oops. I always lose my ability to spell after approximately 1 hour. Okay. And the uptype ones then we're in a basis where we can write them as V dagger, YU diagonal, where this is our old friend, the CKM. Okay. So what that means is that if we're in a diagonal down quark basis, all the flavor mixing is really showing up in effects where we put in the uptype object. And so one can define a quantity that we're going to call lambda FC, that was their notation, for flavor change. This is going to look like the following: YU dagger, IJ. Okay, and this thing, roughly speaking, goes like YT squared VTI star VTJ. Okay, and of course there's other contributions from, you know, the other entries, right? But it's the top one that tends to dominate, as I said. So plus smaller. Okay, and so you can write down, for example, operator structures like the following: Q left, YU dagger to the left. Write D right, YD dagger, YU dagger to the left, etc. And so on. Okay, and anything where you have 2 D rights is just going to be negligible, because you'd always have to somehow connect them via the YU dagger insertion. Okay, like so. Okay. This one is going to have a fermion mass suppression because it's going to go like lambda D for the diagonal, YD diagonal, I guess you could say. right, times the lambda FC, okay, is basically this set of objects in here, okay. So we can write, for example, for our flavor change of 2, so for example, for our friends, the meson mixings, you could write here H effective, again, I'm going to shun prefactors pretty much. You could write QL lambda FC gamma mu, QL, QL bar lambda FC gamma mu QL, okay? And similarly, you can do the same sorts of things for the delta F equals to 1, where you'd have just one lambda FC insertion. So what this tells us is something like the following, and again, a cartoon sort of version. So let's imagine the following sort of process, BS and a blob, and then some kind of gamma, a photon, okay? So for example, in the MSSM, we know there's various loop diagrams that can lead to such a process, okay? In the standard model, we know that these things can happen through a W at the top here, okay? So it's gonna go like VTB star VTS. Now, generic MSSM, one of the many possibilities you have would be, let me draw this more, is to have, for example, the B goes to stop at Targino, okay? And if it's generic MSSM, then there's just going to be some sort of coupling out there, delta TS, which you would know what that is, right? Based on, and then it'd be some function of the stop over the Targino mass, for example, in the loop, right? But if you have MSSM with minimal flavor violation, what happens is this now, the same diagram becomes BTB star BTS. So the idea is that with minimal flavor violation, you can inherit the model. So the idea is the new physics should have quote unquote proper respect for the standard models CKM and GIM suppressions. And if you have such theories with minimal flavor violation, the bounds can be greatly lowered. So more like order 10 TeV or lower, depending on the sector. Okay. So I just wanted to mention that this isn't the only possibility for the new physics, but generally when you violation, there's many, many things that can happen. And minimal flavor violation is a very sort of standard way to try to imagine how this is controlled. And it does allow for the possibility of new physics being there generically at much lower scales. Order 1 coupling. So Heather, how are we doing on the time? Are we almost out?
I think we're a bit over, and there's some questions actually in the chat, so maybe.
Okay, yeah, let's stop here then and we can answer those questions. Yes.
Okay, so here's very interesting questions actually. So one question is, when you set the Yukawas to 0, you've got the U3 to the 5th. Is it anomalous, or is there part of it that's anomaly free?
Yes. Right, so it's not a gauged object. It's just global rotations.
Okay, okay. It's, yeah, so the next comment was that because they're global symmetries, so no gauge anomaly.
That's right.
Is inserting y sub u perturbative because y top is about 1? How does one take care of this case?
Kind of watch for those things, I guess, but I think the thing to remember is very often what happens in these, when you're looking at these constructions, essentially the top Yukawa structure at the end of the day is oftentimes it's coming in, like the first correction term comes in with that what seems to be large object, right? But then it's controlled. It's just that's the first time the top comes in. Okay. So I think you do have to sort of watch for it, but remember there's also heavy objects in here, etc. So the top is a large Yukawa coupling, but it's not 4 pi strength. Okay. It's more like 1. Yeah.
Okay. Why do we have to insert Yukawa matrices between d right bar and d right? Isn't that a singlet under U3 to the 5th already?
Yeah, but the main point is that if we're trying to look for places in which you can imagine there's flavor violating operators, okay, you're trying to understand where the flavor violation might come in. The point is, if we're trying to do the D right to Q left, in minimal flavor violation, and it's sort of a, you have to be a little careful. Obviously, we've chosen purposefully to be in a diagonal down basis, right? So generally speaking, if you wanted to write it sort of in a more complicated, but if you'd like more basis independent way, you'd have both YD, YD dagger, and YU, YU dagger, generally. So you couldn't put those in, but the point is, at the end of the day, when you do the diagonalization, it's going to, the one that depends on just the YD alone is basically we already know about that one. That's already the Yukawa that's already there. We're talking about higher dimensional things eventually that you put in. What structures come in as blocks to when you construct, for example, 4 Fermi operators.
Yeah. Another question, I think I missed it earlier. What makes the B meson sensitive to beyond the standard model physics compared to other mesons?
They're all sensitive, actually, in different ways. I think the B is of interest right now because of the fact that there's experimentally, there's been a number of sort of dedicated experiments looking at them. It's also when you involve the B quark in things, there's many advantages. There's advantages experimentally in the fact that you can identify the B's by various processes, which is not as easy to do with some of the other objects. It's also, in terms of handling some of their uncertainties, I think they're in the heavy quark domain specifically compared to the U and the D and the S and et cetera, and the charms kind of on the border. So they're all sensitive. It just, there's more data in the B system. There's data on the Ds, which are the CU combinations, okay? But it's harder to interpret because quarks involved are lighter, and generally there's going to be more of a non-perturbative uncertainty for them.
So like the hydronic uncertainties are smaller as well.
That's right.
Okay, and to be clear, the minimal flavor violation picture is not on its own new physics, right?
Yeah, I would say it's a constraint on possible new physics. So for example, in a canonical example would then be in a supersymmetric model. So in the MSSM, for example, if you just allowed arbitrary soft breaking terms that you could write down, then generally you could have the possibility of order 1 flavor violation and order 1 CP violation in all sorts of places. And so what applying minimal flavor violation does to, say, the MSSM is to say there's different ways you can implement it. So one is to say maybe all the soft supersymmetry breaking terms are flavor diagonal. Then that means only through the effects of Yukawas and et cetera could you ever have any sort of flavor violating effects. Another option is sort of that somehow their flavor structure is just like that of the scalar part is just like that of the fermion part, right? So in other words, if the squark mass matrices are diagonalized in the same basis as the quark ones, then generally you're not going to have huge problems. Whereas if they're not, then you're going to generally have big effects. So it's a paradigm, I would say, more so than anything else. What you, I think, would really like to see is some sort of dynamical reason why, if you have a new physics scenario, why you should have a minimal flavor violation sort of picture, right? So one example could be sort of minimal gauge mediation in supersymmetry in the MSSM as an example, because everything's sort of flavor, everything's like identity and flavor space, okay, because it's gauge interactions that are doing the thing. And so, whereas in supergravity, for example, and it's just Planck mass suppressed, anything can couple. So in general, you don't have any reason why you'd expect things to be flavor diagonal, or the mass matrix contributions from the supersymmetry breaking part are going to be proportional to identity and family space. Generally, they're not, right? So it's an interesting guideline for theory, and from the point of view of, if we do see new physics, we would know that whatever things have to be, if it doesn't show up in sort of this flavor sector associated with, for example, these B anomalies or some other data that we might see eventually, if it's just some new physics we see elsewhere that could in principle seem like it can talk to these other things, you'd have to understand why is it not flavor changing. And this could be one sort of paradigm to see if you can come up with complete theories that can explain such a thing.
Okay, and one final question. Following Edward's question, it seems there will also be similar Sphaler process, which might partially break global symmetries non-perturbatively?
Yes, I would say so. Yes. Yes. So remember, this is not a real global symmetry of the standard model. This is a approximate one in the limit in which all the Yukawa couplings are turned off. So ultimately, we know it's not an exact one. So eventually, if you like, those spurion fields get background values and the symmetry is broken. This is just when you're talking about writing down, for example, Lagrangian at a fundamental level, it's a way to control how you write down your possible coupling.
So like an educated guess to guide model building so you don't immediately screw everything up.
Exactly, because otherwise you can see it's like a minefield. I mean, you could immediately just be totally in over your head, because you see the standard model flavor pattern, it's very delicate, and generally you put in new physics, it's going to completely disrupt it.
Awesome. Yeah. Okay, any other questions? Oh yes, when global symmetries get broken, we expect Goldstone bosons. Can those be interpreted as the pions and other mesons?
Well, the pions are interpreted as global symmetries associated with QCD sector and sort of the chiral perturbation theory language. As I said, again, here, remember, this is a symmetry only in the limit that some things are switched off completely, and we know they're not. Yeah.
So these are explicitly broken.
They're explicitly broken, basically.
Yeah.
They're not spontaneous. We're just pretending that they are by calling the Yukawa a field. Now, maybe we have, in a more formal theory, maybe the Yukawa is a field, okay, that we then have somewhere, and we figure out how to give it a Bev, and then we'd have to worry about that question in detail. Yeah. But I would imagine in the sort of complete theory where you were looking at such a question, it's sort of unlikely that you'd want some part of that global symmetry to be gauged somehow, and then all the questions that came up before about the anomalies and et cetera would all come into it. Yeah.
Mm-hmm. Okay, awesome. I think we should probably call it a day at this point.
Okay, that's it.
Thanks a lot to Lisa. Tomorrow we start again at 9 o'clock TASI time with a lecture by Kev on neutrinos in astrophysics in the early universe. And then we've got Andre finishing off the neutrino mass models, and then Lisa's final talk at 2 p.m. TASI time, of course, the coffee break as well. And then on Friday, tomorrow afternoon, starting at 3:45, we have the final discussion session with the two people who didn't talk at the discussion session most recently, so Kev and Ben Jones. And see you all tomorrow morning.
All right, thank you, Heather. Thanks, everybody. Bye-bye.